Okay, so moving on to question 39, draw curved arrows to show the flow of electrons responsible for the conversion of the reactants to the products. And the way that your book draws it, it draws it a little bit more explicitly, but this is another way to think about the reactants and the products. So this might be a way that I could give this to you on an exam. And one of the important things is to be able to take this and convert the way these molecules look to the way that your book kind of has them drawn out. In this case, it actually becomes pretty useful to be able to think about the implicit hydrogens on this, bromine substituted alkane. So let's go ahead and draw these guys out. So I'll go ahead and draw out the hydrogens here, here, and go ahead and draw these guys out as well. 1, 2, 3. Okay, and also for the alkene on the right-hand side, your book has all 4 hydrogens drawn out, but it should be obvious to you if you just saw this double bond that there should be a total of 4 hydrogens attached. Okay, so a couple of things to do. Same thing as always is you want to make sure that your charge is balanced on the left and the right hand side of the equation. Overall negative, neutral, so an overall negative on the left, neutral, neutral, negative, overall negative on the right. So it seems like more than likely we've drawn everything properly. So now all we have to do is figure out where that negative charge is going, or how we converted the negative charge on the oxygen to a neutral charge. So let's go ahead and redraw this water. So just to make it a little bit easier to see. So we have this oxygen with 2 hydrogens on it. Okay, and so now thinking about basically what we're trying to do is we're going to try to add a hydrogen onto this oxygen. And the only place we can get a hydrogen is from this alkane. And we're going to end up wanting 1 less hydrogen on the final alkene. So 1, 2, 3, 4, 1, 2, 3, 4. So that seems to indicate that we are indeed losing a hydrogen from the alkane to give the alkene, and that hydrogen is going to go onto the water or onto the oxygen. Okay, and we're also somehow converting this bromine from being neutral to negative. So now all we have to do is let's go ahead and designate one of these hydrogens as the hydrogen that's going to be attached to the oxygen at the end of the day. So we're going to use this hydrogen, totally arbitrary, as our sacrificial hydrogen, and we're going to go ahead and make that new oxygen-hydrogen bond. So to do that, we have to think about nucleophile, electrophile, or in this case, it might be a little bit easier to think about this in terms of acid-base. So our base is going to be the hydroxide, and specifically the oxygen, negative charge, so really, really basic. So we're going to take one of these electrons and make a new oxygen-hydrogen bond using those electrons. So electrons start at the base, electrons stop at the head. And so let's go ahead and say, okay, the final bond between the oxygen to this hydrogen is going to be kind of this pink color. So that's going to be this bond right here. So that's going to be that hydrogen. And so what we also have to do is, so that we do not break the duet rule, we need to break this hydrogen to carbon bond. So we're going to break this bond, and we're going to push electrons onto the carbon-carbon bond. So we get a little bit of a hint from that from this final product. So see how there's 2 bonds here. We have a sigma and we have a pi bond. So we need to form a new carbon-carbon bond somehow. So that's what we're doing in this step right here. We're taking the electrons that used to be in the carbon-hydrogen bond, and we're using them to form a new carbon-carbon bond. So now, at this point, a lot of students will stop, and that'll be the end of it. And that's totally not the correct way to draw all of the curved arrows. Okay? If you stopped this way, what you would be saying is that you would be getting, H2O, which is totally fine, that seems to check out. But then you would be drawing an alkene, something like this. So it should be quite obvious right off the bat what's wrong with this guy. And the obvious issue here is that we have, a carbon with 5 bonds to it. So this is a Texas carbon. This is a carbon that's breaking the octet rule. So this is a very bad scenario. It's an impossible scenario to have. Okay, so this is incorrect, completely wrong. Get you 0 points on an exam. Okay, so what that indicates to you now is that we are not done with all of our bond making and bond breaking above. So the way to actually make this work out just fine is to take a look at the bromine and the product side. And we know that at the end of the day, this bromine needs to be negatively charged. The way to do that is to go ahead and take electron density from this carbon-bromine bond, and we need to put it onto the bromine. So if we actually take a look at all of the valence lone pairs, on this bromine right here, we have 2, 4, 6 electrons. And so to make this bromine negative, we can't just have 2, 4, 6. We need to have another pair. Okay, so that means that this pair is going to be coming from somewhere. It needs to come from somewhere. And this extra pair right here is, and if you're not really sure why this is negative, go ahead and convince yourself by doing a formal charge calculation. Again, these calculations should be really quick, really easy, really fast in your head. Okay. So you need to know valence, you need to be able to do, the valence minus lone pair minus bond to give you the overall charge. Again, it needs to be really, really quick. But now it's obvious that we need another lone pair from somewhere. So the obvious place to get it from is going to be from this carbon-bromine bond. So we have to break this bond as well. Okay, so we're going to take these electrons that used to be in the carbon-bromine bond and push them onto the bromine to give us that negatively charged bromine, and voila, we don't have a carbon that's breaking the octet rule anymore. Okay, so this checks out, and this checks out. Okay, so overall, to actually draw this mechanism, you would have to draw 1, 2, 3 separate arrows. Okay, and this is actually called an elimination reaction. We'll go through these in a lot more detail later on. And depending on conditions, this is one particular type or particular way of drawing an elimination mechanism. Later on, we'll see at least one more way on how to actually make this elimination reaction proceed. But yeah, that's for later. Okay. For now, hopefully this makes sense. If not, it's really worth your time to make sure that this does make sense. The faster this starts to make sense, the easier of a time you're going to have whenever you have to draw mechanisms on exams. Okay, great. Next question.